So when we're talking about work, there's finding the work whenever the force is constant. That kind of work is pretty easy. I do believe you probably did that in physics, and it's easy. All you do when you're trying to find work, if the force is constant, is you do the force times the distance or the measure of whatever you're talking about. For example, determine the work done in lifting a 50-pound object 4 feet. That just means that we're going to multiply 50 because 50 is the force. Most of the time, the force is a type of weight or the amount of weight put into it. In this case, it's pounds. You multiply by 4, so you get 200. And the units are pounds, feet, or feet pounds. So when the force is not constant, there's lots of different things that we can talk about as far as different kinds of laws. Okay? We're going to talk about Hooke's law first, and then we're going to do some things with earth, and then we're going to do Boyle's law, earth, and then we're going to do Boyle's law. There's some other things that I'm still working on, like lifting a chain is another kind of work that is important, and pumping out water, but these are the only three we're going to deal with today. Okay? So Hooke's law says that it is the force required to compress or stretch a spring, and it's proportional to the distance d that the spring is compressed or stretched. F equals kx is the proportional part, where k is the constant of proportionality, depending on the nature of the spring, and x is the distance that it's stretched or compressed. So if you have a spring and its natural length, they call it the natural length, that's just what it looks like when nothing's being done to it. Okay? If you squeeze it together, you're trying to find the work required to squeeze it together to make it a certain length. Or you're trying to find the work required to stretch it to a certain length. That's what Hooke's law is. Okay? And on all of these, because the force changes depending on the length, you have to use an integral. Okay? So you start off by finding what k is, and then we have to use an integral. And we're still going to use the fact that work is force times the distance when we do the integral, but we're going to find k first. Okay, so in number 2, it says, suppose a force of 500 pounds compresses a truck spring 5 inches from its natural length of 20 inches. So we have 500 pounds, and it compresses a spring 5 inches. It says it's the natural length of 20. We don't even have to use that 20. Okay? All right, we're going to start with the F equals kx, and we're going to plug in the 500 and the 5 to find k. 500 is the force. X is the 5. It's the distance. So you get that k is 100. All right. We're trying to find the work, though. So work is the integral of whatever the problem is talking about. If you'll look at the other 2 examples down below, there's different situations and different equations. It's always the integral of those equations. So it's the integral of kx, and we know that k is 100. All right, and then let's figure out what units to put in there, or what numbers should be on the integral. It says find the work done in compressing the spring an additional 5 inches. So it's already at 5, and we want to go 5 more, so it would be 5 to 10. And there should be a dx here. So if I find the antiderivative here, the antiderivative of 100x is 50x squared divided by 2. And we're doing it from 5 to 10. So you plug in 10, you plug in 5, and you subtract. You should get 3,750. Let's talk about the units a second. The length is in inches. The force is in pounds. And so you get inches, pounds. Yes, that should not be over 2 because I've already divided by 2 when I put the 50. I think the answer's still right because I wrote down the correct answer. But it would have been 100 divided by 2 or just 50. Alright, so you start off by finding K. And you use the 750 newtons and the 13 centimeters to get K. So then you're going to do your work, which here it says we want to stretch the spring from 12 to 15. And we can just use 12 and 15. And then Kx, we already know that K is 57.69. We would find the antiderivative, which is 57.69 divided by 2x squared. Plug in 15, plug in 12, and subtract. And because I'm running out of room, I'm just telling you it's 2,336 centimeters newtons. And if you don't carry out the 57.69, you'll get a different answer. Okay, so next kind of example, it's moving a space module into orbit. And some things that they sort of want you to know is that the radius of Earth is 4,000 miles, or something thereabouts. They also want you to know that the weight of a body varies inversely as the square of its distance from the center of Earth. So because of that, the force exerted by gravity is F of x equals c over x squared. So, number 4. A space module weighs 15 metric tons on the surface of Earth. The 15 metric tons represents your force. So that's the F. And then the fact that it's the surface of Earth, that's where the 4,000 comes into play. 4,000 is the X. How much work is done in propelling the module to a height of 800 miles above Earth? Okay, we'll get to that. Let's start with the F of x equals c over x squared. And that's where we're going to plug in the 15 and get c over 4,000 squared. On these problems, you're usually going to get big numbers with lots of zeros. Do the best that you can. You're going to end up with 240 million. So, when we do the work, alright, the work, it tells me that we want to propel the module to a height of 800 miles above Earth. Well, the fact that the radius of Earth is 4,000 miles, that's where you start at. So what do you think the top limit would be? 4,800. So you start where the radius is, and then you add how much more above Earth that they want us to be. And then our equation is that really big number divided by x squared. Alright, although the antiderivative is a little bit more complicated, I do believe that you can still do it. Think of it as 240 million x to the negative 2. So add 1 and divide by it, and you would get negative 240 million x to the negative 1, and that's what you evaluate at 4,800 and 4,000. So you do negative 240 million, 4,800 times 4,800 to the negative 1, minus negative 240 million times 4,000 to the negative 1. And then when you do that, you will get 10,000, distance is miles, and weight is tons. So you start off by plugging in the 25 and the 4,000. And you should get 400 million. And then we do the work equation, which is the integral of something, of 400 million over x squared. And what would the integral be from? So 4,000 to 5,000. Find the antiderivative the same way. So x to the negative 2, if you add 1, divide by it, you get negative 400 million. X to the negative 1, and then evaluate from 4,000 to 5,000. Then you should get 20,000. Our units are miles, and weight is tons, so miles, tons. Okay, last kind of problem is Boyle's law. And the equation itself is very much similar to the one we used in 4 and 5. It's just talking about different situation. The pressure of a quantity of gas is inversely proportional to the volume. So you start it the same way. You use the P equals K over V to find K. Once you find K, then you make your work equation, plugging in K and then solving. So we have a quantity of gas with an initial volume of a cubic foot. It didn't specifically say a number there, but that right there is 1 cubic foot. You need that. And the pressure is 500 pounds per square foot. And it expands to a volume of 2 cubic feet. And we want to find the work done by the gas. Okay. So start off with the initial volume and pressure, which would be 500 equals K over 1, because it's 1 cubic foot. So you get K is 500. So then your work equation is going to be from 1 to 2, because it started at 1 and we want to expand it to 2. Plug in our 500 and divide it by volume. As far as the antiderivative, very similar to the way we did 4 and 5. Well, it's a little bit different because it's not raised to a power. But so what's the antiderivative of 500 over V? It's natural log, yes. So 500 natural log of V, and then evaluated from 1 to 2. So you'll plug in 500 natural log of 2 minus 500 natural log of 1. And you get 346.6. And here's our units, feet, and then pounds.